Welcome back. This is a large topic of budgeting, and we're focusing on forecasting in this phase. This video is going to look at one aspect of forecasting, which is regression analysis. And we should be able to explain and use regression analysis to estimate future data. Regression analysis finds the line of best fit computationally. Let's just remember the line of best fit. Here we have a scatter diagram, and we can see the x-axis and the y-axis and a series of data that has been put onto the graph. The line of best fit is a way of roughly establishing a linear trend between the data that we have. The linear trend is important. By linear it means straight line, and it can be represented algebraically. Y equals A plus BX, often known as the linear equation. And what regression analysis will do is to derive the linear equation using statistical techniques much more accurately than using the line of best fit on the scatter diagram. We can calculate the variables A and B here using what look like quite complicated formula. These formula you do not need to memorize. These formula will be given in any examination where you need to use them. All you need to do is to know how to derive A and B using the formula. Let's just look at an example. Here we have some historical data. It's on its sales during the last year in each of its region and the corresponding number of salesperson. So the question's telling us there's a relationship between the level of sales in units and salespersons. The first thing we have to do is develop our linear model, develop our linear equation using figures for A and B, and then use that to forecast what sales will be with 16 salespersons, and then finally to test the validity of the model using 18 salespersons. So let's start at the beginning with the data we've been given. We've been given number of units of sales and the number of salespersons. The first thing we have to decide is what is going to be X and what is going to be Y. Y is the dependent variable. It's dependent on X. X is the independent variable. It is Y that we want to forecast, because that is dependent on the number of units of X that we're going to use. In this case, we want to forecast sales, so that is Y, and the model implies that that is dependent on the number of salespersons. So we can work out what is X and what is Y. Once we've done that, we can start to establish some of the key data that we need in our solution. We're going to first add up our columns, and we've got the sum of Y, which is 1466, the sum of X, which is 79. There are two other columns that we need if we are going to work out the solution. We need X squared and we need X, Y. you can see that these are terms in the formula. Terms in the formula. So let's go back to the example. We're going to calculate just a few of these to show you the principle. So we've got x squared, 11 squared is 121, 12 squared is 144. X times y, 11 times 236 is 2596. And then try again, 12 multiplied by 234, we've got 2808. If we go on to one that I prepared earlier, we have our columns. These have been added up, all 4 columns, and now we're going to put them into our equation. I'll need a bit of space for this. So in my equation, I'm going to start with n. n is 6. There are 6 pieces of data. And I'm going to multiply that by the sum of x, y. 19,736. Put that in brackets, because from that I'm going to take away, back to the equation, sum of x, 79, times the sum of y, 1466. And that is going to be divided by, go back to the formula, n is 6, multiplied by the sum of x squared, which is 1083, minus, brackets, the final bit is the sum of x, 79, squared. If we do these equations bit by bit by bit, so we have 6 times 19,736, which comes to 118,416, and then minus the next part, which is 79 times 1,466, 115,814, divided by 6 times 1083, 6489, minus 6241, and then we finish off those part of the equations, and we come to 2602 divided by 257, and that comes to 10.12, and that is B. In an examination where you have a written question, do make sure that the stages of your computation are clearly laid out. I know that you can do these calculations in your calculator, but if you just put this number, B equals 10.12, in your answer without showing how you got there, then you will lose some key marks. We always need to see the workings when you're looking at regression analysis. So once we've got B, we move on to A. And for A, we've got 2 key terms here and here. Sum of y divided by n, sum of x divided by n. And they are averages. So let's have a look. We'll have A equals our sum of y divided by n, which equals 2,4,4133. minus our 10, 12, multiplied by the average of x, which is 13.16, again recurring. So that's recurring and that's recurring. When we calculate that all the way through, we get A to equal 111.09. We can now put all of this into our linear equation. And here we have our linear equation y equals 109 times 10x. So we can use it for our forecasting. If there were 16 sales persons, we would use the model that we've developed. And the number of salespersons, x, would actually be 16. So we substitute that in. And there we get the answer. $273 units. Please note this would be a whole number. You wouldn't put 273.01 units. We would round it appropriately. And so I would in this case certainly round it down, because we want to be cautious about the number of sales that we're going to predict. If we look at the next question, we're going to, for 18 salespeople, oops, 18, not 16 again, and that will get us to 293 units. Not 293.25, you can't have 0.25 of a unit. We'll show it in whole numbers. Now the interesting thing with 18 salespersons is that's one of our pieces of data. So we can actually look at the degree of error in our model. So the actual sales, in the model for 18 salespersons equaled 298. We've got a degree of error. So our degree of error, 298 minus 293, and that is a degree of error of 5. Always when we have absolute figures, they're not telling us very much. It's much easier to have this as a percentage. So we take this as a degree of percentage of our actual data, 200 and of our forecast data, 293, because we're looking at the error in the model, and that's an error of 1.7%. which is not significant. It's a low degree of error. So we can be fairly happy with the quality of the model. There are a few provisos. The first thing I have to say, given the model we're using, we have got 6 pieces of data. And even though we're happy with the validity of the model, we have to be very concerned that there is not enough data for us to actually make an accurate model. This is not sufficient. In practice, we often talk about a minimum of 30 pieces of data to produce a statistically accurate model. I'd also be cautious when I'm forecasting far away into the future. I have used historical data. And I'm going to ask myself, is that going to be valid moving forward? That data might reflect my internal and external environment for the next 2 or 3 months. But if I start forecasting a year in the future, are those internal and external conditions going to still be holding true? Will technology have changed? Customer demand? My working practices? Any changes like that could make my historical data not valid. So really, I can't rely for the long term. I've got the linear assumption. I'm assuming that relationships between y, the dependent variable, and x behave in a linear fashion. Now, if you think back to some of your other studies, think back to economics, we talk about things often working in a curvilinear fashion, particularly when we see efficiencies like economies of scale, when we increase the volume of activity. So it may be that a linear assumption is not valid. So we have 3, and there are more, but we have 3 key assumptions associated with this model. Saying that, this is my key problem area, because with my other 2, I can say that those 2 are valid for the short term. Over a limited period of time, we are going to say that if nothing significant happens, my historical data can be shown to represent the future, and the linear assumption is often valid over the short term. But I've only used 6 pieces of data. The other thing to bear in mind when we're using models is the data that we use in the model when we're forecasting. We have in this question a particular range, and it's often called the relevant range, and the range is here, and it's between 10 and 18 salespersons. And any forecasting that we do within that range has a degree of validity. But when we start to move outside the range, say to forecast sales for 25 persons, how many sales will they generate? Here we are extrapolating. We are trying to predict way outside the relevant range. Are the relationships between sales and salesperson still valid when you start to have a critical mass of, say, over 24? I don't know. It always bears looking at if we're going to extrapolate outside the range. Does the model still hold true? Well, that's enough for this video. We will be looking at regression in further videos. Thank you very much.